All right, here's our game plan for this journey. We'll start with the spectrum of virtualization, move into Hyper-V, and then check out KVM as our open-source engine. From there, we drop down to containers, explore tools beyond Docker like Podman and LXC, and finally, we'll peel back the magic.
Section 1. The Spectrum of Virtualization. Let's dive right into the big picture of how we evolved from running directly on bare hardware to the complex environments we use now.
If you look at our evolution, you can pretty clearly see the fundamental trade-off we've been making over the years. We started entirely on bare metal, running apps directly on an operating system with absolutely zero isolation. Then came virtual machines, utilizing a hypervisor. Now this gave us incredibly strong isolation, but at a huge cost. It's heavy. You're running an entire guest OS for every single application. Moving down the timeline, we hit containers, where applications just share one host kernel. This trades that strict, heavy isolation for incredibly lightweight, fast startup times. And finally, we arrive at the modern cloud standard, running lightweight containers inside strongly isolated VMs, so we can basically get the best of both worlds.
Section 2. Hyper-V, slicing the hardware. Let's take a look at how we actually slice up the hardware itself, starting with Microsoft's enterprise-grade Type 1 hypervisor.
There's a really fascinating architectural showdown here between two industry giants, VMware's ESXi and Microsoft's Hyper-V. ESXi uses what's called a fat hypervisor model. Its kernel contains its own device drivers, which makes it rock-solid and robust, but it means you are locked into a very strict, specific hardware compatibility list. Hyper-V takes the exact opposite approach. It uses a thin hypervisor, where the host Windows OS handles all the hardware drivers. The massive upside here? Any hardware that works with Windows works with Hyper-V. But the critical downside, and it's a big one, is that if the Windows host OS crashes, every single one of your virtual machines crashes right along with it.
And that brings us to some vital terminology you're going to hear engineers throw around. Microsoft doesn't just call them VMs internally. They call them partitions. Your main management OS, let's say your Windows 11 desktop, is the root partition. The actual VMs you create, those are child partitions. And the absolutely crucial thing to understand here is the difference between enlightened and unenlightened partitions. An enlightened guest OS knows it's being virtualized, so it uses highly optimized drivers to talk directly to the hypervisor. An unenlightened partition, though, it has no clue it's a VM, which forces the hypervisor to use full, agonizingly slow hardware emulation.
So let's look at how this builds into a very practical real-world mystery. If you've ever installed Hyper-V on a Windows machine, just by checking that little box in Windows Features, you know it absolutely demands a system reboot. But why? Why does turning on what looks like a simple software feature demand a hard restart of the entire system?
Well, the answer is actually wild. During that reboot, your host OS literally gets pushed up. It is physically separated from the bare metal, and the Hyper-V hypervisor slides right underneath it. Your host Windows OS suddenly becomes just another partition, the root partition, sitting on top of the hypervisor. This hardware-level takeover is exactly why Hyper-V natively conflicts with Type 2 hypervisors like VirtualBox or VMware Workstation. They are all fighting to exclusively own the CPU's hardware virtualization extensions.
Section 3. KVM, the open-source engine. Now let's shift gears away from Microsoft's proprietary world, jump into the open-source Linux ecosystem, and look at KVM.
Now, KVM is not just a single program you run. It's actually a trio of tools working seamlessly together. Think of it kind of like a car. KVM itself, the kernel module, is the engine. It manages the heavy lifting of hardware acceleration. QEMU is the car's chassis. It's the emulator that actually handles the binary translation and device emulation at runtime. And finally, you have libvirt, which is the dashboard. It's the management API you interact with to control your networking, storage, and memory. You really need all three working together to drive this virtualization vehicle effectively.
And a super important call-out here. While QEMU all by itself can emulate entirely different architectures using pure, slow software emulation, KVM strictly requires hardware virtualization extensions to function. If your CPU doesn't have VTX or AMDV enabled in the BIOS, KVM simply cannot create VMs at all. It heavily leverages that hardware to achieve near-native speeds.
Section 4. Containers, slicing the OS. We're dropping down a layer now, transitioning from that heavy hardware virtualization to lightweight operating systems. Welcome to the world of containers.
I want to start this section with an awesome concept inspired by Julia Evans. Containers aren't Marek. It is so incredibly easy to fall into the trap of thinking containers are just tiny, ultra-fast virtual machines,
But they aren't. They're simply isolated Linux processes. Actually, with just about 15 lines of a bash script utilizing core Linux features, you can build a basic container completely from scratch without ever even installing Docker.
So what are the actual gears turning behind the scenes to create this container illusion? Well, it all boils down to two native Linux kernel features, namespaces and control groups, or C groups for short. Namespaces isolate what a process can see. They give the process its own totally isolated view of the file system, network interfaces, and process IDs. Inside its little namespace, a process actually thinks it's PID1. Meanwhile, C groups limit what a process can use. They put very strict boundaries on exactly how much CPU or memory that process is allowed to consume. You combine those two together, slap on some security profiles like AppArmor or SELinux, and boom, you have a container.
Let's look at how Docker actually orchestrates this by tracing the command chain right under the hood. When you type docker run, your Docker CLI sends a request via a REST API to the docker.sock file. This talks to the Docker daemon. But here's the massive twist. Docker doesn't even run the container. Not at all. It hands the job off to Containerd, which manages the images and networking. Then Containerd hands it down to a tiny tool called Runc. And Runc is the thing that actually interfaces with the Linux kernel to create those namespaces and C groups for the final container process.
Section 5. Beyond Docker, Podman and LXC. Because containers are really just a standardized way of using built-in Linux kernel features, Docker definitely isn't the only player in the game. Let's expand our toolkit.
When we break down the broader container ecosystem, you have LXC and LXD focusing on system containers, meaning they treat a container much more like a lightweight VM, running a full operating system init process with multiple services running inside. Then you have Docker, which focuses on application containers, ideally just one single process per container, managed by that heavy background daemon we just talked about. And finally, you've got Podman. Podman is also for application containers, but it's completely daemonless and was designed from the ground up to run rootless, offering much better security out of the box.
And when you take all this theory and put it into practice in a real sysadmin lab, these distinct behaviors become super apparent. When you install Docker, for instance, it's pretty invasive. It directly manipulates your IP tables, which can completely bypass local firewalls like UFW if you aren't careful. Podman, on the other hand, runs smoothly as your regular user without ever needing to type sudo. And LXC implements its security by mapping all the root processes inside the container to really high, unprivileged user IDs, like user 1 million, on the actual host system.
Section 6. Peeling back the magic. Let's bring this explained to a close by focusing on the real security implications of this isolated process reality we've just uncovered.
We know that Docker relies heavily on a socket file /var/run/docker.sock for all its internal components to communicate. And it is incredibly common in lab environments to use management tools like Portainer. To make those tools work, you usually map that docker.sock file directly into the container. This lets the container talk directly to the host's Docker daemon. Which leads me to this final, terrifyingly critical thought. If we know for a fact that containers are absolutely not magic, that they are literally just regular processes sharing the host's kernel, what do you think happens when a supposedly isolated process gets full access to that Docker socket? Well, it results in a complete container escape. That process can just command the daemon to spin up a brand new container with full root access to the underlying host, completely shattering the entire illusion of isolation. It really forces you to stop and rethink exactly how secure your environments truly are, doesn't it? Thanks so much for joining me on this explainer, and I will catch you on the next one.